Hi all, welcome to my YouTube channel Know About Embedded System. In today's video we're going to understand one more important topic that's called as ADC, and it is called as analog to digital converter. So before starting today's video, if you're a new viewer to my channel, kindly subscribe my channel and gain the knowledge on embedded system. Let us start the video here. ADC, that stands for analog to digital converter. So basically why this ADC is required in our embedded system. So without ADC, it is not at all possible to design any embedded system. Okay, so let us discuss in detail. Analog to digital converter, the input for ADC is going to be an analog input and continuously varying input, and then output from the ADC will be a digital. That's nothing but binary. So why this is required, let us explore. So if you consider our embedded system application, if you consider any embedded system application, here you can see, so ADC plays a very important role in our embedded system. So without ADC, it is not possible to design any embedded system, because ADC will convert our analog data, like analog information such as real world data such as temperature, humidity, pressure, wheel speed, and so on. There are many physical parameters we can convert into digital, and we can give it to the processor for processing and storing the data. If you do not use ADC, let us assume we don't use ADC here, it is not at all possible to give any analog data to the processor directly, because processor or a memory will not understand any analog data. That is what I told. It is not possible to design any embedded system without ADC. So ADC plays a very important role in our embedded system to convert analog to digital, analog information to the digital. So what is an ADC? I have already told you what is an ADC. ADC stands for analog to digital converter, which will convert our analog information to the digital so that your microprocessor can understand, and we can do the processing, and also we can store your information in our memory system. So what are the different analog data in our physical world? Example, I have taken some of the things here, like a temperature, pressure, humidity, acceleration, speed, and so on. These things, whatever you're seeing, these things will be analog in nature. Your sensor will sense in analog, and it will get passed on to the ADC, and ADC will convert analog information to the digital. Then why we need ADC? Answer already I told you why we need ADC. ADC is required because the analog in nature, most of the parameters, most of the physical signals will be in analog in nature. Right, that point we have to understand here. So digital system cannot understand, or they cannot read your analog informations which are available in the physical world, such as your temperature, humidity, speed, and so on. These things cannot be read directly from the analog devices or analog sensors. So there should be a device to convert into digital. Second thing, sensors always produce analog data. So currently whatever we have in our semiconductors, we have two types of sensors, analog sensors and digital sensors, but most of the time we use analog sensors. Okay, so analog sensors will produce analog outputs or analog signals. Okay, so that's why we required ADC, and then we need to do some processing. In our embedded system, we're supposed to do some performance. Like for example, if temperature is exceeding some threshold level, we have to turn on some heat fan, or we have to turn on some cooling system, or we want to turn on some alarm system. Like this, some of the processing we're supposed to do. This is very difficult to do with analog signals. So that is why we required ADC. So these are all very important things why we required ADC. Then how the ADC will convert, like what are the different stages, this I'll explain in detail later. So you should know the input for the ADC will be analog data, and output will be your digital data, or you can say binary data. And this ADC will follow, like any type of ADC will follow at least three types of three stages. One is first one is called as sampling, then second one is called quantization, and third one is called as encoding type. All these three steps I'll be explaining in the next slide. As I told you already, there are three major steps are there. One is a sampling, one is a quantization, and one is called encoding or coding mechanism. So let us understand one by one what is this. Sampling. So what do you mean by sampling? Sampling means converting analog data to a discrete with a predefined time interval is called as sampling. Sampling is a process of converting continuous signal. So try to understand the definition here. So ADC will take, it's here they're talking about a snapshot. The snapshot is nothing but discrete signal. Converting continuous signal into sampled signal. The ADC will take a snapshot or nothing but samples of analog signal or voltage with a regular time interval. So with a predefined time interval, and it will be defined by Fs. So what is Fs? Fs stands for sampling frequency or sampling rate. So what do you mean by sampling? Sampling is nothing but taking the samples of continuous signal or analog signal is called as sampling process. Okay, and it will be represented by Fs. Fs stands for sampling frequency. So then the Nyquist, there is one theorem is there that's called a sampling theorem. So what it says, the sampling theorem. Theorem says that the sampling frequency should be greater than or equal to at least 2 times of Fm. So here you can see, so he's talking about two parameters here. One is a sampling frequency and one is message frequency. Your sampling rate should be greater than or equal to at least 2 times of Fm. So what do you mean by FM? FM is nothing but frequency of analog signal or frequency of your input signal. Input analog signal is called as FM or a message signal frequency FM. So what Nyquist theorem says that sampling frequency should be greater than or equal to 2 times of FM. So this is related to sampling process. So what do you mean by quantization? So quantization means it is going to divide your discrete signal into different voltage levels. Discrete signal or a sampled signal will be divided into voltage. It will be equated to its equivalent voltage is called as quantization. I'll explain with respect to the image later. There is a diagram for that. Then encoding. The final step of ADC is called encoding. So in this process, your analog signal voltage will be converted into digital form or in the binary form. Is called as encoding. So like 3 important steps: sampling, quantization, and encoding. Yeah, so these 2 images, whatever you are seeing, this is called the sampling. The first diagram what you are seeing, this is called as sampling. Here you can see that I have a continuous signal here. I have continuous signal here, and this continuous signal is sampled with a regular predefined time interval. The continuous signal is sampled into predefined time interval, and this process is called as sampling. Okay, and after sampling, the ADC signal will be passed on to the quantization process. In the quantization process, here you can see it looks like this. In the quantization process, each sampled signal will be equated to its equivalent voltage like this. Each signal will be allocated or equated to one voltage value, maybe 1 volt, 1.25, 1.3, 3.5, something like that. Each discrete value will be allocated or equated to its equivalent voltage. This process is called as quantization. So let us understand with the definition. The sampling, as I already told, sampling is a process of taking the samples periodically with the signal snapshots is called as sampling. Rate at which signals are converted from analog to discrete is called as sampling rate, and the process is called as sampling process. Then we have quantization. Quantization means, just now I told, equating your discrete signal to its equivalent voltage is called as quantization. The process of mapping continuous analog input to its finite and a discrete set of digital values is called as quantization. So here, so these are all my sample signals, and these sample signals I am going to assign, or I am going to equate to its equivalent voltage. This process is called as quantization. Okay, so this is a basic three principles, basic three stages of your ADC. Now let us move. So we have one more important thing with respect to ADC, that is called as resolution. Very important, and in the most of the interview this question also will appear. What do you mean by resolution of an ADC? So what do you mean by resolution? Resolution is defined in two different ways. The first the first and foremost is the resolution can be defined in this way. It represents the smallest change in the analog input voltage when analog signal is detected. It represents the smallest change in the analog input voltage that ADC can detect. Is called as a resolution, and also this ADC can be defined in a standardized way in this way. The ADC resolution defines with a number of bits. The ADC resolution refers to the number of discrete analog values that ADC can represent. Okay, so different analog it refers to discrete analog voltages with the different levels. Okay, so that can be represented by this value. The different levels can be represented by 2 power n. So what is n? N represents the number of bits of your ADC, whether your ADC is 8-bit or 10-bit or 12-bit, like that. Okay, so like this, in a two different way ADC is defined, and if you have more number of bits, then you will have a higher resolution. Higher bit resolution can result with a more number of levels and more number of bits. If you have more number of bits, resolution will be more. Okay, so let us see with one example. So this is a formula for your ADC resolution, very important formula for the ADC. ADC resolution is equal to V reference divided by 2 power n. Very straightforward and simple equation. Resolution is equal to V reference divided by 2 power n. Okay. What is n? N represents number of bits, and V reference is nothing but input voltage. So let us take one use case here. Consider V reference I am taking as a 3.3 volts, and consider n is equal to 8, and when you do the calculation, so V reference 3.3 divided by 2 power n, nothing but 256, and it is going to produce 0.0128, nothing but 12.8 millivolts. So I have considered second example here, n is equal to 10, and when I do the calculation here, it looks like this, 0.00322. So if when I write it in a millivolts, it's going to be 3.22 millivolts. So what is the meaning of what we can conclude with this is, when you have more number of bits, so this thing n is equal to 8, in the previous calculation n is equal to 8, and in the present calculation n is equal to 10. So what it says, resolution is more. For 10-bit ADC, the resolution is 3.22 millivolts, and for 8-bit ADC, it is 12.8 millivolts. So that means whenever you want to interface ADC, we have to select with a higher resolution and higher number of bits. Okay, so this is called as resolution. So coming to the types of ADCs, there are 5 types of ADCs are available. They are like this. We have SAR ADC, very important and most popular ADC is SAR ADC, stands for Successive Approximation Register ADC. Then we have Sigma Delta Dual Slope ADC, and then we have Pipelined ADC. So most popular ADC is SAR type, that stands for Successive Approximation ADC. So let us understand detailed working of this SAR ADC with the block diagram. So this is a block diagram of your SAR ADC, very simplified block diagram. In this block diagram, so we have these many blocks. The main important thing lies in SAR, that stands for Successive Approximation. This is the main building block of your ADC, that stands for SAR, Successive Approximation Register. Then we have DAC here, digital to analog converter. Then from the DAC, one input is given to the comparator here. So this is your comparator. One input is given from the DAC. For the DAC, input is given from the SAR. So SAR will give digital data, DAC will convert to analog, and that analog input is given to the comparator here. one input of the comparator, and second input to the comparator is taken from the analog input. Here you can see this is my analog input here, and from this analog input we have given here into the sample hold circuit, and this sample and hold circuit will produce your sample signal. Here you can see this is my sample signal, and sample signal is having the analog voltage of 10 volts. Okay, so one input our DAC output is given to the comparator, and one more input to the comparator is your sampled input. Okay, so what happens here is so whenever DAC voltage is falling, okay, so before that you should understand how the SAR will work. So SAR will keep the MSB as 1. This I'll explain in the next slide better. So this is the block diagram, and these are all the building blocks: sample hold, successive approximation, digital to DAC, and then comparator, then controller. So this is a control logic. So this is a simplified block diagram, and let us see how it works. So how it works. Okay, so there are 5 to 6 steps are there. Initialization of sample and hold circuit. As I told you already, the first step says the initialization of sample and hold circuit. Nothing but analog input is given here, and then with the help of the sample and hold, we got sampled signal which is in analog in nature. Okay, then the second point, MSB test. So what do you mean by this MSB test? MSB test means the SAR will initiate the MSB with a 1 and then rest all the bits to 0. What SAR will do? SAR will initiate MSB bit to 1 and rest all the bits to 0, 0, and then this digital data will be given to the ADC like this. The digital data will be transmitted to the DAC, and DAC will produce the equivalent analog voltage. And let us consider here one use case. I'm getting 8 here. So 8 volts analog DAC, let us assume the DAC is producing 8 volts of output. Okay, and input voltage is 10 volts. The DAC is producing 8 volts. So now input voltage is greater than your DAC output. So now what comparator will do? Comparator will generate one high to low signal, and it will also tell to the control signal to read in the bit which we have set. So now initially we set bit number MSB to 1, right? So since my input voltage is greater than my DAC voltage, and control signal will produce high signal to retain the MSB which we set. So this is the first process, and the similar to that, continuously subsequent bits will be checked in an iteration way. So we have 8 bits, so we will get around 256 combinations here. 2 power n combinations we will get, and your SAR will produce continuously. It is going to check with the different combinations of bit, and once all combinations are verified, and when all combinations are completed, then SAR will generate one control signal that is called as done bit, or it is also called as EOC. EOC stands for end of conversion, and done bit is also called as end of conversion. So both we will use done bit or end of conversion. Once the completion is completed, all iterations are completed, and this SAR will produce the digital data in the form of binary, like this, something like this. Finally, the SAR will produce, and it will store it into one of the register called as ADC data register. Okay, so this is how internal ADC will work, especially SAR ADC. Okay, so important thing I have explained in this block diagram. I hope this is clear to all. Now let us see what are the applications of ADC. Everyone knows that already. Without ADC we cannot design any embedded system, but most of the time our ADCs we can see in our smartphones, digital cameras, and audio equipments. So we will be seeing all these type of applications like smart mobiles, digital cameras, and so on in our day-to-day life. In our medical instruments like ECG mechanisms and MRI, blood pressure monitoring or blood sugar level monitoring. So in that applications also we will see. industrial systems like monitoring a temperature, monitoring a pressure, monitoring other physical variables, right? So monitoring some of the very vehicle speed. All these are coming under our applications of ADC. Scientific measurements, like in the laboratories, precise whenever you want to measure scientific values with a very precise way, we will use ADCs, and also in the communication finally. So in our day-to-day mobile communications or your voice communications, we're going to use ADCs. With this, I just want to end my video here. Please like this and subscribe to my YouTube channel, Know About Embedded System. Let us meet again.